The next speaker is Mark Simkin. He will tell us about the power of NAPs, compressing or proofs via collision-resistant hashing.
Yeah, thanks for the introduction. So this is a joint work with Katharina Budgust. And the main topic of this talk will be Sigma protocols, which is a special type of interactive proof system. So let's just quickly recall what it is. So here we have a prover and a verifier. The verifier wants to be convinced that some statement is in some language, and Sigma protocol is identified through its kind of structure in the sense that the prover sends a message, the verifier sends back a uniformly random challenge E, and the prover responds with some response Z. So it's shaped like a sigma. And at the end, the verifier is either convinced that X is an L or X is not an L. And we want several properties of such a sigma protocol. So the first one is completeness, meaning that if everybody behaves honestly, then the verifier will accept. Yep. And the second one is special soundness, which basically says that if I have that there exists an extractor that takes two transcripts as input and outputs some W, and what we want is that if these are two accepting transcripts that have the same first message but different challenges, then the witness is indeed a witness for X being in the language. And lastly, we have honest verifier zero knowledge that says that if we have a simulator that is given a uniformly random challenge, and for this uniformly random challenge, without knowing the witness for X, it can output completed to a valid transcript with a first and a last round message. And what we want is that the simulator obviously produces something that is indistinguishable from a transcript that I would get from a valid real execution. Okay, so one thing that is maybe slightly less common, but is still kind of a strengthening of this notion is that of strong honest verifier zero knowledge. Here I now require that I don't only sample E uniformly at random, but I also sample Z from the corresponding distribution, so the last round message. And I only generate the first round message with the simulator, and I do this in a deterministic fashion. And this may seem like a somewhat stronger notion than the one that one usually has for Sigma protocols, but if you look at kind of the standard approaches of how you prove Sigma protocols, usually you do exactly that. You have a second round message as input for the simulator, you sample the third round message, and then you compute the first round message correspondingly. So many natural protocols already satisfy this notion. And indeed, in principle, you can transform any Sigma protocol into one that satisfies strong honest verifier zero knowledge if it starts with honest verifier zero knowledge. Okay, so what languages do I maybe want to prove statements about? So there's many possibilities, but one that is kind of expressive, but at the same time kind of specific enough to maybe provide efficient proof systems are disjunctive statements. So here I have statements x2 and x1, and what I want to show is that either x1 is in the language or x2 is in the language. And here for simplicity, it's the same language. This obviously can be generalized to have multiple statements. And it turns out that this is kind of specific enough to solve much more efficiently than using a generic proof system often, but still general enough for applications like ring signatures, which are used in blockchains like Monero, or electronic voting, where I maybe want to prove that I voted for one out of several valid candidates. So this is the statements that we focus on here. And kind of already in the 90s, we know how to basically take a Sigma protocol for the language and transform it into a Sigma protocol for disjunctive statements. So here I put the Kramer, Damgard, Schönemeyer reference, but there's also DeSantis, Crescenzo, Preciano, and Young around the same time that made very similar observations. And this is a very simple transformation that kind of produces a protocol that has a linear communication overhead. So if I want to prove 1 out of n statements in the language, then the overhead of my resulting protocol will have a multiplicative factor of n in the total communication complexity. And then the natural question is well, how much communication complexity do I need? So if I use structured hardness assumption like D-log or lattices that already have some kind of nice linear properties, then often I can get around this linear communication and I can compress things very nicely, so I get small communication complexity. But I do rely on these structured hardness assumptions. I can also go via a route of something called MPC in the head, where I get something below n, but still large in terms of communication complexity. And lastly, I can go into the world of PCPs and IOPs, but there I kind of use really complex machinery to do an OR proof, and I get polylog communication. Now, what we did in this work is we basically say, ask, can we find a simple transformation of sigma protocols to sigma protocols for disjunctive statements that has sublinear communication complexity? And like we give kind of like a partial answer to that in the sense that if we have a sigma protocol that satisfies strong honest verifier zero knowledge and you have collision-resistant hashing, then you get a sigma protocol for disjunctive statements with logarithmic communication overhead. So this is kind of like the main result of the paper. And along the way, kind of like what we like use as like tools is like we introduce a notion of non-adaptively programmable functions, which is like a distributed point function in disguise, which basically says I have, let's say, a PRF, and I at some point want to reprogram one of the outputs. Well, then this tool allows you to do that. And another thing that we show is that rejection sampling can be explained. So I won't go into too much details about this here, but think of rejection sampling as a way of sampling from a distribution. But maybe later on I'm given a sample from the distribution and I want to provide the random coins that will output that sample. And I don't want to know whether I first sampled or first explained. So we show that if you can do rejection sampling, then you can also explain it. So you can also go the other way and recover the random coins. Yeah, it's okay. So to understand our construction, it's sensible to understand the CDS construction because ours is conceptually a pretty small modification of that. So we have a prover and a verifier, and now the prover wants to convince the verifier that one out of several statements is true. So let's say the first statement is true. So what it will do is it will sample the first message honestly. It will fully simulate the transcripts for all other of the end statements where it doesn't have a witness. It will provide the verifier with the first round messages. It will receive a challenge. It will make sure that all the individual challenges E1 to En sum to E, and it will compute the corresponding Z1 for E1, and it will send back both the challenges and the Zi, the responses, where the verifier will check that all these transcripts are accepting transcripts, and it will check that the EIs sum to E. So if we look at this protocol, then we can see that the communication complexity here is linear in N, because effectively I run one proof execution for each N in the full. So like I send N values of A, N values of E, N values of Z. So if you want to make it somehow sublinear, we want to compress all of those. Okay, so let's compress all of those. So the first one, we'll just send the hash. So now instead of sending all the values A1 to AN, we just send a collision-resistant hash value of those values. Now for the second and the third round messages, the simulator, what it does is, the prover, what it does is it picks the EIs and the ZIs at random and it computes the AI with the simulator. But now we will not pick EI and ZI at random, we will pick them pseudo-randomly. So we just pick a short seed, expand it into those responses, and then compute the corresponding AIs. And lastly, in the end, we will not send all the EIs and ZIs, but we will just send the seeds that we use to generate those challenges, those messages. And the challenge that you kind of run into is that like this approach kind of like conceptually almost works, but the problem is that like obviously you cannot just pick completely random challenges. They need to satisfy something because you're proving knowledge of, or like you're proving that X is in the language. So you need to be able to like pick those seeds, but afterwards to reprogram them at one position. So you need to reprogram the seed that generates the EI values to have a specific E1 value, and you need to reprogram the pseudorandom, the seed that generates the ZI values to output Z1 at location 1. So that kind of brings us to this like notion of non-adaptively programmable functions. And in general, you know, you would like to have something like a privately programmable function. So it's a PRF where you pick a key. Later on, you're given an input and an output, and you reprogram that key to that output. So it turns out that constructing them is pretty hard. So you need either like very hard assumptions or like also complex constructions. So this is not really what we want, especially not if we want to build a construction from collision-resistant hashing. But like the main observation here is that we don't need this tool. So in a privately programmable PRF, I generate the key and then I find out where I want to reprogram the key. But here it's different. When I generate the key, I already know where I will reprogram it. I just don't know to what value. So it turns out that this simplifies the problem massively, in fact so much that you can just build it from one-way functions. And I will not have time to go into details of how to construct it, but if you know something about distributed point functions, it's basically, a point function is a truth table that is all zeros with a single entry that is 1. A distributed point function is a non-trivial secret sharing of this truth table, a 2 out of 2 secret sharing. So everywhere where there is a 0, if the shares XOR to 0, they're the same. If the shares XOR to 1, then one of them is 0, one of them is 1. Well, now you interpret them as a truth table. Now you have 2 truth tables that are the same, but at one position, one of the truth tables is 0, one of the truth tables is 1. So like depending on what you want to program, you pick the correct truth table and send the seed for that truth table. So that's kind of like the whole construction. Another thing that I won't be able to mention here is that like these explainable samplers are needed because the functions that you will construct this way, they will produce functions that output, let's say, uniformly random bits. But if you look at Sigma protocols, you don't need bits. You, for example, need uniformly random graphs or like some other objects. So you need to make sure that they come from the right distribution. And when you reprogram the function, that you also reprogram kind of like in the right way. So that's where the explainable samplers come in. So you put them on top of the naps, and then you get the thing that you need. Yeah, thanks. Questions?
The construction of the non-adaptive programmable function is quite interesting. Can you give like a naive or simple example to let us know how to construct something like that?
Yeah, so as I said before, so like what you would basically think of is that like, you know, you have naively what represent a truth table, like you could pick a random function by just picking the truth table of the function. And now if you want to reprogram it, then you just change the value that you want to reprogram. But this is not a great construction because like, you know, to send a truth table, that's a lot of communication complexity, and we want to have something with small communication complexity. So now you kind of like want a way where you can compress the truth table but still reprogram it at one position. And distributed point functions kind of like have a different name, but they're exactly that if you look at them from the right perspective. So this is kind of how you get them.
Could you please elaborate on what you mean by sending the seeds? Because I see like 2 issues. First of all, if you send the seeds for Z, then it's not quite clear that the verifier won't be able to distinguish which instance was the right one. And on the other hand, if you want to sample, if you want to get the for the challenges E, it's not a problem. It looks like a problem potentially for the answers Z. Where
sure. So the intuition is that what a distributed point function provides you with some security guarantees, and what it basically says is that you don't know where in this truth table, if it's not secret shared, where there is the 1. So in other words, if you have the 2 shares, then you don't know in which position the 2 truth tables differ. So this in some sense means that like you don't know at which location did I reprogram the output. And this is why even if I give you the key that I reprogrammed for the Z values, you cannot tell where I reprogrammed. So this is kind of like, yes, this is important that this is hidden in the seed. And then just to clarify, I send the short seed, and then the verifier will kind of like evaluate this PRF or this NAP on value 1, 2, 3, 4, 5 to obtain the values Z1, Z2, Z3, Z4, Z5. Does it clarify it?
How does it compare the final protocol? Is it?
Oh yeah. So like now, what is the communication complexity of this protocol? Well, you basically send the hash value, so like that doesn't really depend on n at all. And then you send the keys. And now if you use kind of like the distributed point function from one-way functions, then you basically get a logarithmic dependency on n rather than a linear one. Yeah, in terms of, yeah, does that answer your question?
But concretely, is it going to be similar efficiency? Let's say for discrete log,
yeah,
you take the discrete log solution and your solution apply.
Oh yeah, no. Okay, so here's an open question. Make it concretely efficient because, so I can tell you what is the concrete problem. The issue is that the construction that I described allows you to reprogram 1 bit. But like what you really want to do is like, you know, you want to generate many bits and you want to reprogram 1 value. And the way we do it right now is we basically say, well, just, you know, concatenate a bunch of 1-bit PRFs, then you get a many-bit PRF, and then reprogram all the bits. But then you get obviously like in the key size, you get a multiplicative factor that depends on the length of the output. So this is like makes it like, if you try to then, let's say, plug everything in and like compare it to like lattice-based ring signatures, then you will end up with something not massively big, but slightly larger than the state of the art. So, but if you could get rid of that, like, then you would get something much smaller. Yeah? Yes, okay, cool.